very good morning to all of you. I welcome you to the second session on metal forming processes. This session will be dedicated towards all the processes which come under the broad specialization of metal forming. So, first session we had 3 lectures. In those 3 lectures we discussed regarding the powder metallurgy. Now, in this second session that will be overall covering 9 lectures. In these 9 lectures we will go through the various aspects of metal forming. Now, metal forming is one of the important manufacturing processes. As we might have seen when we go to the market or we go to some manufacturing industry, we see that the metal is being formed into different shapes. As we do sometimes, if we take a hammer and start hitting a metal piece, we can see that under the impact of the hammer or the forces that we can apply with the help of a hammer, the shape of the metal can be changed. So, the basic principle of metal forming is that by the application of force the metal is plastically deformed. So, in this session or in this lecture we will discuss regarding the metal forming fundamentals, and in the subsequent lectures during this particular course on metal forming we will see that what are the different types of metal forming processes, what are the various numerical formulations, and what are the basic process details of metal forming processes. So, today we will start with the very fundamentals of metal forming. As we go through this lecture, we will see what are the basic manufacturing processes, where does metal forming fit into the manufacturing processes, then what are the basic principles of metal forming, what are the various metal forming processes, then we will go and discuss regarding the hot working and cold working of metals. So, in order to start, let us first understand what are the various basic manufacturing processes. So, the basic manufacturing processes, as we have earlier also seen in powder metallurgy, that there are 5 different types of basic manufacturing processes. These manufacturing processes are casting, deformation processes or metal forming processes, machining, joining. In joining we include fastening, welding and adhesive joining. Then we come on to the finishing operations. Now, all these processes are used to convert a raw material into a final product. We have certain raw material, the material can be cast iron, it can be steel, or it can be any other form, it can be plastic, it can be any kind of wood. So, any raw material is converted into the final product using any of these basic processes. So, we have already discussed in the basic lecture on powder metallurgy that casting can be either it can be done using expandable molds or it can be done using permanent molds. Similarly, deformation processes we have already seen rolling, forging, extrusion are some of the deformation processes which are used to convert the basic raw material. The basic raw material in case of these deformation processes can be, it can either be a bar of material, it can be a rod, it can be a sheet metal, it can be a plate. So, all these type of materials or the raw materials using any of the deformation processes will be converted from its raw form to its final form, that is in the form of a product. Then coming on to machining, in machining already we have seen the material is removed in the form of chips. The chips may be of different types, it can be continuous chips, it can be discontinuous chips, or it can be the discontinuous or continuous chips with the built up edge. Then we come on to the joining processes. Joining processes either can be permanent joining processes or these can be temporary joining processes. Under joining we have fastening, welding and adhesive joining. Now, welding whenever we do, we make a permanent joint, wherever we make use of fastening, we make use of a temporary joint with the help of nuts and bolts. Then why finishing processes are required, already we have discussed. Again, just to give a brief summary, if we require a very good surface finish or we require some surface characteristics, some anti-wear coatings, then we go for the finishing operations. Different finishing operations are grinding, lapping, honing, super finishing. So, there are different types of finishing operations which can be used to impart the surface characteristics to the product. Now, as we see, we convert a raw material from its raw form into the final product form. So, there are number of processes which can be used to do this job. So, the job basically is to convert a raw material into the final product. But the problem arises that there are a number of manufacturing processes out of which we have to choose that which manufacturing process we should use to convert the raw material into the final product. So, selection of a manufacturing process to produce a product is a trade off among a number of variables. So, what are these variables? These variables are material of, we can say material of the product that we are going to produce. It can be wood, it can be stainless steel, it can be cast iron, it can be aluminum, it can be titanium. Now, the material will play an important part in selection of a manufacturing process. The second is shape, size, complexity, volume, and there are many other factors which we may have to consider in order to finally select a manufacturing process. So, already starting with the first, I have told the material plays a very important role in the selection of a manufacturing process. There are like the metal forming process can't be used for brittle material, because if brittle material we strike it with a hammer or we subject it to a combination of different forces, the brittle material may fail under the impact of forces. Similarly, all the materials are not castable, all the materials are not machinable. So, depending upon the material, we have to see whether we are going to cast it or we are going to machine it, or we can use any of the basic process of metal forming to convert that material from a raw material into its final form. Coming on to the shape also plays a very important role. Now, if we want to make a very big product, it can be made using the sand casting process, but if we choose a permanent die casting process where the size of the die will be a limitation. Moreover, if we want to finish a very large size of a product or a very large size, then we have to put it on a machine. Now, if we put the big size of a product on a machine, it will be very difficult for the machine to handle a very big product, as we have seen or we can see that the limitation of the machine is the size of the bed or the size of the job it can hold. So, in order to machine a very big product, we need to have a very big machine, so which may not be a feasible or a viable operation. So, size of the product is also an important criterion for selecting a manufacturing process. Similarly, the shape of the product is also very important. Now, in powder metallurgy, we have seen that if the shape is very intricate, the powder may not flow into the intricate parts of the die and we may not get the product according to the desired quality. Moreover, if the shape is very complex, then we may not be able to make it using a die casting process. We may use a split type of a pattern and different types of molding procedures to make it by sand casting, or there can be other processes to make it. So, the size as well as the shape of the product will define that what type of a manufacturing process we should select for converting that particular material from a raw stage to the final stage. Similarly, the complexity in the operation also plays an important role. Then coming on to the volume. Now, the volume of production is also very important. As we can see that in sand casting we have to make a mold, because it is expandable mold type of casting. So, when we have to make number of times the mold, the procedure will be time consuming as well as the lead times will be more. Wherever in permanent die casting operation, there is a permanent die, the metal is injected into that die in the molten stage and we get the final product. So, the volume or the production rate is extremely good in case of permanent die casting, whereas it may be comparatively less in case of sand casting. Similarly, there are other processes which may be producing the products at a very faster pace as compared to the other processes which may be converting the raw material into the final product at a very slow pace. So, the selection of a particular manufacturing process to convert a raw material into a final product depends upon different factors. The broad factors or the major factors are material, shape of the product, size of the product, complexity and the volume. Already it is mentioned there are many other factors which will affect the selection of a manufacturing process. So, till now we have seen that in order to convert a raw material to final product, we have different options, different manufacturing processes are there, and depending upon certain variables, we have to make a trade off among all these manufacturing processes to decide that which manufacturing process is going to be used for converting a raw material into its final form. So, in this series of lectures, we are dedicating ourselves towards two important aspects of manufacturing, that is powder metallurgy as well as the metal forming operations. So, we already have discussed 3 lectures on powder metallurgy. The next 9 lectures will be dedicated to metal forming operations. So, today we are going to start with metal forming fundamentals. Now, deformation processes. As we can see, if we want to change the shape of a metal, we can hammer it, we can apply some forces and it will convert into the shape that we want. Moreover, if there is a rod of a bigger diameter and we want to change it into a wire of smaller diameter, we can use a die, we can pass the rod through that die, and in the subsequent steps we can convert from a larger diameter to a smaller diameter. So, there are different types of deformation processes that are there. So, what are basically deformation processes? Deformation processes exploit a remarkable property of metals. What is this remarkable property? Which is their ability to flow plastically in the solid state without deterioration of their properties. Now, the metals have this property that they can flow plastically without deformation and without substantial change in their properties. So, these deformation processes will make use of this property of the metal. With the application of suitable pressures, as a simple example I have mentioned, as the blacksmith, or we can see a jeweler, he also gives a shape to the gold and the blacksmith gives a shape to the iron or any particular material by hammering it. So, with the application of suitable pressure, the material is moved to obtain the desired shape with almost no wastage. Almost no wastage, this is an important point to address in case of deformation processes. As we have seen different manufacturing processes, machining removes the material in the form of chips and then gives us the final shape. In case of deformation processes, we are not going to remove any material, it is only the changing in shape of the material with the application of suitable pressures. So, with the application of suitable pressures, the material is moved to obtain the desired shape with almost no wastage. The required pressures are generally high and the tools and equipment needed are quite expensive. Large production quantities are often necessary to justify the process. Now, the equipment in case of metal forming or the metal forming processes are extremely of high rate. So, it is not that all the equipment or all the processes incur very high cost. There are certain processes like when we forge with the help of a hand or hand forging, the process is not that expensive, but wherever we go for die arrangement or punch arrangement, so the material of the die, the size of the die, the intricacy of the product often necessitates that we need to have a very good die, so that whatever is the shape of the die, whatever is the surface finish on the inner walls of the die is replicated on the final product. So, the die wall or the lining of the die wall or the size of the die often results in a high cost. So, this high cost can only be justified with a large production volume. So, if the production volume is substantially large, then the initial cost of establishing or the initial cost of setting the process will be spread over a number of products. But if the production volume is substantially less or it is comparatively less, then whatever cost we have incurred on setting up of the machinery or the setting up of the machines will be distributed only on small volume of components. So, the cost of the components will be extremely high. So, in order to justify the high cost of establishing or the high cost of setting up of a metal forming plant, we should be able to justify it in the cost wise. So, the cost should be comparatively or the cost should be justified with a large production volume. Now, as we have seen that the metal is pressed under suitable pressures and we get the desired shape. So, when we press the metal undergoes different types of stresses. So, this diagram shows that what are the different types of stresses a block of metal can undergo. So, we can see that either we can have simple uniaxial tension, or we can have biaxial tension, we can have triaxial tension, then we can have biaxial tension and compression, a combination of tension and compression we can have, then we can have biaxial tension and compression, then we can have uniaxial tension, we can have biaxial compression, we can have biaxial compression as well as tension. So, we can have two axes, we can have compression and then we can have tension also. Triaxial compression can be there, we can have pure shear, we can have simple shear with triaxial compression. So, in here the point to mention is that whenever we go for a tensile testing or the material is subjected to tensile load, we see that the material fails after the necking has started. We fix one end and then we pull the other end, and in between there is a necking region which develops, and after the necking region the material fails. Whenever we apply a compressive force, we have a, suppose we have a rod like of specimen, then we will apply a compressive force, and if the slenderness ratio or the aspect ratio is not suitable, then it will buckle under the applied compressive loads. So, buckling will be the limiting factor for compressive loads and necking will be the limiting factor for deformation under tensile loads. So, either the material will fail after the necking or the material will fail after the buckling. Another case to be studied here is that if there is a rod and neither we are compressing it nor we are applying tensile load, but we are just rotating it. So, when we are rotating it or we are subjecting it to a shear load like this, then under the shear load it may fracture. So, there is a limit to the deformation. It is not that if we take a metal we can elongate it to as much as length as possible, or we can compress it to as much as possible. There are limits to elongation as well as compression. Similarly, there is a limit to the torsion also. So, what are these limits? These limits basically are necking, buckling as well as fracturing. So, whenever the necking starts, the material is going to fail. Whenever the buckling takes place, we are not going to get the desired shape of the product that we have designed the process for. Similarly, whenever fracturing takes place, the material is going to fail. So, there is a limit to the deformation and there are limiting factors up to which the deformation can take place. So, these are certain states of stress that metal undergo during the deformation process. Now, as the metal is deformed into a useful shape, it experiences stresses such as tension, compression, shear or various combinations. So, as we have seen in the previous slide, there are different types of combination of stresses that are possible, that states of stress that the metal undergo during deformation we have already seen. So, now as the metal is deformed into a useful shape, it experiences stresses such as tension, it can undergo compression, shear or various combinations, like we have seen biaxial tension, biaxial compression, or it can undergo a combination of these types of stresses. Now, there are different types of processes that are possible using these state of stresses. Now, the metal will undergo these type of states of stresses under different types of operations. Now, we will see that what are the different types of operations and under what operation the metal undergoes what type of states of stress. Now, the first operation is rolling. Now, what is the rolling operation? In rolling operation, there are 2 rolls or there can be 4 rolls. It depends upon the type of mechanism that we have chosen for rolling operation. So, here the diagram that is shown here, there are 2 rolls which are rotating and which also have a center distance which has been fixed depending upon the final dimensions of the shape that we want to make. So, we can see that there is a bigger rod that is going inside and there is a smaller rod that is coming outside. So, what type of stresses are prevalent here? The stresses are biaxial compression. The metal is being compressed from 2 sides or it is undergoing compression, that is biaxial. So, in rolling process where we are reducing the cross section of the raw material and we are getting the desired cross section after the rolling. So, we the metal has a state of stress, that is biaxial compression. Similarly, there are other metal forming operations like forging. Now, this diagram shows the forging operation. Now, what is forging? Already one example I have told, whenever we take a metal either in the hot or in the cold condition and hammer it, then that process basically is called forging. Now, forging can be hand forging, or we can use different types of presses to change the shape of the metal into the desired form. So, forging operation basically has triaxial type of compression stresses. So, there are 3 axes, or triaxial means from 3 sides it will have compressive stresses. Now, we will see different types of other processes. We have already seen 2 processes, first one was rolling and second one was forging. Now, we come on to the third process, that is extrusion. What is the basic extrusion process? In basic extrusion process, this is the metal is pressed from this side and this is the die opening. Now, die opening decides the shape of the metal or the shape of the final product that we want to make. Now, if we want to make a rod, this will have a circular cross section. Now, depending upon the opening of the die, we will get the desired output. So, the metal here is pressed from this side and it comes out of the opening. Now, this can very easily be correlated to our morning process of brushing our teeth. Whenever we go and brush our teeth, we take a tube and we press it from one side and the toothpaste comes out from the other side. Similarly, in this process, we press the metal here and it comes out through the opening or the aperture or the die here. So, whenever the metal is pressed, we get a final product. So, the final product or the shape depends upon the die opening. So, what type of stresses are present here? These are triaxial compressive stresses. So, basically this extrusion process can be of 2 types, either it can be forward extrusion or it can be backward extrusion. In case of forward extrusion, we push the metal from this side and the metal comes out from the opposite side, like here. In case of backward extrusion, there is a opening at this particular section and the opening decides the shape that we want to make. So, we will pressurize the metal, or we will apply pressures from this side, and the metal, instead of coming out from this side, will be coming out through the opening in this direction. So, basically the extrusion has 2 different categories. The first one is the forward extrusion and the second one is the backward extrusion. Similarly, the another process or the metal forming process is swedging. In swedging, the different types of stresses are biaxial compressive stresses. So, different state of stresses are prevalent under different manufacturing operations that fall under the category of metal forming operations. Now, deep drawing is another metal forming operation. In case of deep drawing, we see this is the shape that is being drawn. The color of the metal is shown here. This colored portion is showing the metal which is being deep drawn, and this is the punch which is drawing the metal down. So, in case of deep drawing, we make different types of shapes of sheet metal using the process of deep drawing. In case of deep drawing, in flange of the blank biaxial tension is prevalent, and in flange of the blank biaxial tension and compression is prevalent. In wall of the cup simple uniaxial tension is there. So, we can see the state of stress depends upon the shape or the final shape of the product that we are making. In certain sections the state of stress will be different, and in certain sections the state of stress will be different. So, in case of deep drawing, we can see that in flange of the blank biaxial tension and compression is present, and in wall of the cup simple uniaxial tension is present. So, deep drawing is another operation or another metal forming operation which is used to convert a sheet metal into the desired shape of the final product. Now, already I have told, if we want to reduce the cross section of a particular rod, then we can use wire drawing or tube drawing. So, wire drawing or tube drawing can be done. Here we can see the pressure or the load or the force is applied at this angle, not at this angle, but at this end of the workpiece, and we are pulling the material through the die opening. So, in case of wire drawing and tube drawing, biaxial compression and tension is present. So, we can see there are different types of states of stresses, a combination of state of stresses which are prevalent whenever a material is deformed plastically under the applied pressures or the applied loads to convert it from one shape into the another shape. Now, in case of straight bending, now straight bending we can see the load is applied, the arrows show in the direction in which the load is applied. So, at the bend biaxial compression and biaxial tension are present. So, we have seen different types of metal forming operations starting from rolling, forging, then we have seen different types of deep drawing operation, tube drawing, wire drawing, straight bending. So, there are different metal forming operations which are used to change the shape of the metal, and during this change of shape of metal, the metal undergoes different types of state of stresses which have been shown. So, different processes undergo different types of state of stresses. So, we have seen that straight bending for example undergoes biaxial compression and biaxial tension. So, all these processes are basically undergoing the process of plastic deformation. So, in plastic deformation in metal helps to convert the shape from a raw material into the final form. So, what basically now we will go through what happens during the plastic deformation of metals. In plastic deformation in metals, metals basically all of us know these are crystalline in nature, and these consist of irregularly shaped grains of various sizes. So, crystalline materials are made up of different types of grains which have irregular shapes. Each grain is made up of atoms in an orderly arrangement known as lattice. So, grain further is made up of atoms which have an orderly arrangement, and this orderly arrangement is known as a lattice. Now, the orientation of atoms in a grain is uniform but differ in adjacent grains. Now, within a grain if we see the atoms are arranged in a oriented manner or they have a particular orientation, but in adjacent grains the orientation of the atoms may not be same and the orientation is usually different in adjacent grains. Now, as we have seen the basic structure of a metal, it is crystalline, it is made up of grains and orderly arrangement of grains, that is called a lattice. We can once again see the metals are crystalline in nature and consist of irregularly shaped grains of various sizes. Each grain is made up of atoms in an orderly arrangement known as a lattice, and then the orientation of atoms in different grains will have different orientations or they are not uniform. The orientation is not same for all the grains. Now, the basic metals, how they are made up of, there are different grains. Now, how the plastic deformation takes place? Now, when a force is applied to deform it or to change its shape, a lot of changes occur in the grain structure. These include grain fragmentation, movement of atoms and lattice distortion. So, whenever a force is applied to deform it or to change the shape of the metal, different types of changes will take place in the grain structure of the metal. So, what will happen, either the grains will fragment or there will be movement of atoms or there will be lattice distortion. So, all these will aid in the plastic deformation of the metal. Now, slip planes develop through the lattice structure at points where the atom bonds of attraction are the weakest. Now, slip planes will be formed wherever the bond of attraction between the atoms is weakest or the atom bonds of attraction are the weakest and whole blocks of atoms are displaced. So, we see whenever we change a shape of a metal, the sheet is like this, we bend it like this. So, the shape is changing from straight, we are making a bend like this, we are making a L type of section. So, physically we can see that the shape is changing, but what is happening within the metal, that we should understand. So, there are formation of slip planes that develop through the lattice structure at points where the atom bonds are the weakest and whole block of atoms are displaced. The orientation of atoms, however, does not change when slip occurs. So, the orientation of atoms will remain same. Now, in order to deform the metal permanently, the stress must exceed the elastic limit. As we have seen that already I have quoted, whenever we take a metal, we stress it under the loading, or we apply a load, or we applied a tensile type of loading on a piece of metal, the metal will stretch and a neck formation will take place. So, if we plot this process on a piece of paper, that we call as a stress strain curve. So, this stress strain curve will give us the elastic limit, after which the metal will plastically deform. So, to deform a metal permanently, the stress must exceed the elastic limit. At room temperature, the metal is in a more rigid state than when at a higher temperature. So, it is easier to deform a metal in a hot stage than in a cold stage. Thus, to deform the metal, greater pressures are needed when it is in a cold stage, when as compared to when metal is in a hot state. So, this difference between hot state and cold state we are going to discuss in detail, and this is a difference between hot working of metals and a cold working of metals. What are the advantages of hot working? What are the limitations of hot working? What are the advantages of cold working? What are the disadvantages of cold working? So, advantages, limitations of hot working and cold working we are going to see in detail. So, it is easier to work a metal in a hot state, and more pressures are required when we are working with a metal in a cold state. So, it is easier to work in a hot state, but more pressures are required when we need to work in a cold state. So, the amount of deformation that a metal can undergo at room temperature depends upon its ductility. So, it depends, if a metal is ductile, it can undergo certain amount of plastic deformation. If a metal is not ductile, if it is brittle, then it will not undergo that much amount of deformation, and it may deform slightly, and after that it will have a brittle fracture. So, it depends upon the property of ductility, that how much deformation is going to take place for a metal. Now we are going to address another important point, that is strain hardening. So, what basically is strain hardening? Whenever a metal is formed in a cold state, so we are talking about cold working here, there is no recrystallization of grains. So, the grains will not recrystallize because we are not raising the temperature. There is a recrystallization temperature above which the process of recrystallization will take place. If we are working in a cold state, we are working below that temperature, and the process of recrystallization is not going to take place. So, whenever a metal is formed in a cold state, there is no recrystallization of grains, and thus recovery from grain distortion or fragmentation. Already we have seen, when metal deformation takes place, grain fragmentation is one of the common phenomenon. So, grain distortion or grain fragmentation does not take place while in cold working. As grain deformation proceeds, greater resistance to this action results in increased hardness and strength. The metal is said to be strain hardened. So, hardness and strength increases and the metal is said to be strain hardened. So, when the grain distortion or grain fragmentation is not taking place in the cold state, the metal may get strain hardened. So, different types of metals and alloys will undergo different types of plastic deformations. So, pure metals can withstand greater amount of deformation than metals having alloying elements. Why? Because alloying elements increases the tendency and rapidity of strain hardening. So, whenever we are adding an alloying element to the pure metal, then there are chances of strain hardening and the plastic deformation may be less. So, metal having larger grains are more ductile as compared to metals having smaller grains. So, we have seen that how plastic deformation takes place: formation of slip grains, grain fragmentation, grain distortion, and then depending upon the type of the material, if it is pure metal, then it can undergo greater amount of plastic deformation. If alloying elements are added, then the plastic deformation may not be that much. Then we have seen that if metals have coarser grain size or the grains are larger, then they are more ductile, and if the grains are smaller in size, then the ductility will be comparatively less. So, plastic deformation we are subjecting a metal to be, a metal is subjected to plastic deformation, and then we are converting it from a raw material to a final product. Now, as we have seen that it is easier to work when the metal is in a hot condition, and we need greater amount of pressures when the metal is in a cold state or a cold position. So, now we will briefly see that what are the hot and cold working of metals. So, basically starting with cold working. What is cold working? Cold working basically is plastic deformation of metals below the recrystallization temperature. So, the plastic deformation is taking place, no doubt, but it is taking place below the recrystallization temperature. So, as we have seen that recrystallization or the grains are not distorting and too much of fragmentation is not taking place, it is below the recrystallization temperature. So, it is generally performed at room temperature. So, we are not heating the metal to an elevated temperature, it is generally performed at the room temperature. In some cases, slightly elevated temperatures may be used to provide increased ductility and reduced strength. As we have seen that whenever we heat the metal, it becomes ductile as well as the strength also reduces. So, if under certain circumstances we need to work on a metal whose ductility is not up to the desired levels, we may slightly increase the temperature of the metal, but it will never go beyond the recrystallization temperature. So, slight increase in temperature is possible, but it will not increase the recrystallization limit. Now, cold working in comparison with hot working, there are certain advantages of cold working. Now, as we have seen basic manufacturing process, now selection of a basic manufacturing process to convert a raw material into a final product is a trade off, and the trade off is among different variables that are material, size, shape, or it can be complexity or the volume of production. Similarly, when we are deforming a metal, whenever from those broad category where we have 5 different basic manufacturing processes, we come on to another a simple category or a subcategory of basic manufacturing processes, that is deformation processes. Now, within deformation processes, we can either go for a cold forming operations or we can go for a hot forming, or we can, in other words, we can say either we can hot work the metals or we can cold work the metals. Now, depending upon different advantages and limitations, we have to make a decision, either we have to go for hot working or we have to go for cold working. So, there are relative advantages and limitation, and depending upon the final specifications of the product that we are going to make, we will choose either of the two, either we will go for hot working or we will go for cold working. Now, hot working in comparison to cold working has certain advantages, it has certain limitations. Similarly, as we are seeing in comparison with hot working, the advantages of cold working are, the first one being no heating is required. So, whenever we have to change the shape of a metal using hot working or cold working operations, we have to either heat it or we have to work at the room temperature. So, in cold working we are going to work at the room temperature. So, no heating of the metal is required. So, as we have seen, volume of production is directly related to the cost that we have incurred in setting up of the equipment. So, setting up of the equipment also includes a furnace where we are going to heat the metal. So, if heating is required, there is additional investment in the form of a furnace, whereas in cold working we do not require to heat the metal. So, when heating is not required, the furnace is not required, so the cost incurred at the initial setup will be comparatively less. So, no heating is required in case of cold working. Better surface finish is obtained. So, if better surface finish is obtained, we may not be requiring any of the subsequent finishing operations. Finishing operations will add to the cost of the final product. So, if we are getting the product in the near net shape and no further or subsequent finishing or machining is required, then the cost will be comparatively less. So, if the surface finish is good, we need not go for machining and finishing operations. Then better dimensional control is achieved. no secondary machining is generally needed. So, already in the second point I have explained that if the surface finish that we achieve is considerably good, then subsequent machining and grinding and lapping and honing or any other finishing operation is not required. So, in cold working, the three basic advantages over hot working are that no heating is required in case of cold working, better surface finish is obtained in case of cold working, and better dimensional control is possible in case of cold working, which is not possible using the hot working operation. Then product possess better reproducibility and interchangeability. So, interchangeability is an important concept wherever we are going for mass production processes. So, whenever we go for mass production, we need to have the concept of interchangeability. So, the products that are made using cold working, they are better reproducible, moreover they have the property of interchangeability. Why this property of interchangeability is coming into picture? Because of the better dimensional control as well as a very good surface finish, which is possible using the process of cold working. Then the products that we are making using of the cold working process, they have better strength, better fatigue properties, and the wear resistance is also very good. So, wear properties of material is good, the strength is also good, and moreover the fatigue characteristics are also good. So, fatigue characteristics basically come into picture if we have some surface cracks. So, if there are certain small cracks of micro size present on the surface of the final product, whenever it is applied, whenever it is used under cyclic loading or it is used under any kind of load where the load is varying with time. So, the chances of the propagation of that crack is possible. So, that crack when it will propagate after some cycles of loading, after some time, there are chances of the failure of the product. So, the fatigue characteristics of the material that we are forming, that we are producing with the hot or the cold working operations should be very good. So, here in this point we have seen that better strength, fatigue and wear properties of the material. So, the fatigue characteristics or the fatigue properties of the product that we are making use of by the cold working operations are very good. Then the directional properties can be imparted. So, directional properties basically means the property of anisotropy. So, either the material will be isotropic or the material will be anisotropic. So, if we want to have certain properties in one particular direction, those properties can easily be imparted using the cold working operations. Like we can see that the crane hook, the hook of a crane which is used to lift the load, can be designed in such a way that it has certain directional properties along the cross section of the hook. So, now depending upon what type of properties are required in the hook, we can design the hook, and those kind of properties or the directional properties can be imparted using the process of cold working. Then contamination problems are almost negligible. Why contamination problems are negligible? Because sometimes we see some kind of scale is formed on the surface of the metal. So, why that scaling takes place? Because at elevated temperature the product may react with the atmospheric oxygen or it may react with the environment to form certain type of scale. But here, as the temperature is not an elevated temperature, the temperature is not above the recrystallization temperature. So, that property or that surface finish or the scaling is avoided, and the surface finish that we get is up to the desired levels. Moreover, the contamination or the deterioration of the surface or the oxidation of the surface which is possible at higher temperatures is avoided using the process of cold working. So, we have seen that there are certain advantages of cold working operations over the hot working operations, but it is only one side of the coin. There are certain limitations also which are possible using the cold working operations. So, what are these limitations? Higher forces are required for deformation. So, whenever the metal is at an elevated temperature, its ductility increases, its strength decreases. So, reduced strength, increased ductility will help to form the metal in the desired shape. But in case of cold working, we need, there is no elevated temperature. So, at room temperature when we are working, higher forces are required for deformation. So, the equipment or whatever machine we are using for the cold working operation should be very sturdy. It should have the resistance to different types of vibrations that are generated, and it should not break under the applied load. So, sometimes there are maybe some cracks in the bed of the metal or the bed of the machine. So, that may at some later stage under some loading, because this is not a single operation, it is a cyclic type of loading that is coming always. We are pressing or we are using the hammer or the punch to change the shape. So, under this kind of cyclic loading, sometime if the bed is not sturdy, it may break. So, higher forces are there. So, the machine should also fit into the domain of these, avoiding the vibrations and avoiding the fatigue type of fractures. So, in whenever we are going to make use of a cold working operation, higher forces are going to be encountered, and the machine that we are going to use for cold working should be able to sustain those kind of forces. Then heavier and more powerful equipment is required. Already in the first point it has been explained that heavier and more powerful equipment is required in case of cold working operations. Then whenever we are making use of cold working, the less ductility is available. So, ductility or the deformation property is less. So, in order to increase the ductility, what we can do, we can slightly raise the temperature in order to improve the ductility of the metal. So, cold working has a number of advantages over hot working, but there are certain limitation areas which have been addressed in this slide. Now, there are other cold working limitations, like metal surfaces must be clean and scale free. Already we have discussed that the metal or the surface of the metal that we are getting after the cold working operations is free from any kind of contamination, but before working we have to make it sure that it is clean and there is no scale present on the surface of the metal. Moreover, in cold working operations sometimes strain hardening occurs, and this may require intermediate annealing. So, now intermediate annealing I am not going to explain in detail that what is the process of annealing. It is basically raising the temperature and then cooling the material or the cooling the product in order to remove the effect of strain hardening. So, strain hardening is a property that may develop when we are cold working the metal. Then undesirable residual stresses may be produced. Now, these residual stresses that are produced during the process of cold working may later on affect the in service performance of the product. So, these residual stresses sometimes may result in a failure of a material or the product that has been made using the cold working operations. Now, we come on to the warm working operations. So, we have seen the cold working operations, what is cold working, how it is compared with hot working operations. Now, the comparison basically was in terms of advantages and it was in terms of limitations. So, cold working has certain advantages over the hot working. Moreover, it has certain limitations which have to be removed if cold working has to be carried on a particular raw material to convert it into the final shape. In between the cold working as well as the hot working, there is another subcategory of metal forming operations, that is warm working. So, basically what is warm working? Metal deformation carried out at a temperature intermediate to hot and cold forming, or the cold working is called warm working. So, intermediate temperature, it is not very high, it is not very less, or it is above the room temperature, but below the recrystallization temperature. So, the metal deformation that is carried out in the at the intermediate range between cold and hot working is the warm working. Now, compared to cold working, warm working offer several advantages. As we have seen the advantages and limitation of cold working in comparison to hot working, now we will see the advantages and limitations of warm working as compared to cold working as well as compared to hot working. Now, warm working basically as compared to cold working has following advantages: lesser loads on tooling and equipment, already limitations of cold working we have seen. The machines should be heavy, they should be able to sustain the loading. So, in case of warm working, lesser load on tool and equipment is present. Moreover, greater metal ductility, the ductility is improving in case of warm working, which was considerably less in case of cold working. Fewer number of annealing operations are required as strain hardening takes place. So, immediate annealing is required after cold working, but here fewer number of annealing operations are required because of less strain hardening. Now, warm working compared to hot working, also warm working offers certain advantages. Now, what are these advantages of warm working as compared to hot working? These are lesser amount of heat energy is required because we are slightly elevating the temperature, we are not going beyond the recrystallization temperature. Better precision of components is there. So, the precision or the accuracy or the surface finish or the dimensional control is better. Lesser scaling on parts. So, no scale formation on the surface of the parts take place. Lesser decarburization of parts. So, decarburization is also less whenever we warm work a metal as compared to the hot working. Now, with warm working already I have mentioned the better dimensional control is there, better surface finish is obtained using the warm working operations, lesser thermal shock on tooling. Now, thermal shock basically is whenever the tooling is coming in contact with the elevated or the workpiece at an elevated temperature. So, some kind of thermal shock may take place. So, here as the temperatures are less, the thermal shock on tooling is also comparatively less. Lesser thermal fatigue on tooling, and so greater life of tooling. So, the fatigue life or the life of the tooling is more as compared to the hot working tools. So, whatever tooling we are using for hot working, the life is considerably less as compared to the life of the tools or the life of the dies that we are making use of in warm working operations. So, we have seen till now under hot, cold and warm working, what is cold working, what is warm working, how cold and warm working are related to hot working in terms of their advantages as well as in terms of their limitations. Now, coming on to the third and the last subcategory of metal forming operations. Like I have already told, metal forming or metal deformation processes can broadly be categorized into three different subcategories, that one cold working, warm working and hot working. So, hot working, what is basically hot working? Plastic deformation of metal carried out at a temperature above the recrystallization temperature. So, important point to mention here is that we are working on the metal at an elevated temperature. The limit of that temperature is above the recrystallization temperature, and whenever we are working above the recrystallization temperature, we will call that metal forming operation as a hot working operation. Now, under the action of heat and force, as the temperature is an elevated temperature, it is above the recrystallization temperature. So, under the action of heat and force, whenever the atoms of a metal reach a certain higher energy level, so atoms will reach a higher energy level, the new crystals start forming. This is called recrystallization. So, we have seen that recrystallization temperature is a limiting factor to distinguish between hot working and cold working. What is recrystallization? Just I will summarize once again. Under the action of heat and force, whenever the atoms of the metal reach a certain higher energy level, the new crystals start to form, and this is called recrystallization, and the temperature at which this happens is called the recrystallization temperature. So, whenever we are working above this temperature, it will be categorized as hot working. Whenever we are working below this temperature, it will be characterized as cold working. So, when this happens, the old grain structure deformed by previously carried out mechanical working no longer exists. So, whenever this recrystallization takes place, old grain structure that has been deformed or that has been formed by previous working or the previous cold working or hot working, that will no longer exist, and instead new crystals which are strain free are formed. So, strain free crystals will be formed after the process of hot working. So, whenever we are raising the temperature above the recrystallization temperature, the old grain structure that has been deformed earlier will be removed, or it will no longer exist, and new crystals will be formed, and these crystals basically will be strain free crystals. Now, hot working, in comparison with cold working, the advantages of hot working are that there is no strain hardening. So, we have seen that strain hardening takes place in case of cold working, and strain hardening will limit the further deformation, and when the material has strain hardened, the deformation or whatever changes that we want to make will be limited. Lesser forces are required for deformation, as at an elevated temperature we have seen that the ductility is improved, the strength is reduced. So, lesser forces are required for deformation. Moreover, greater ductility of material is available. Already we have seen at elevated temperatures above the recrystallization temperature, the ductility that is available with us is considerably more. So, if the ductility is more, the deformation that is possible in the metal is considerably higher. So, greater ductility of the material is available, and therefore, more deformation is possible. Now, we have seen that cold working and hot working are two important processes for converting a raw material into a final product. So, we have seen that how hot working compares to cold working in terms of its advantages. Now, we have seen there are three distinct advantages of hot working over cold working. So, there are other advantages possible with hot working. So, these hot working advantages are favorable grain size is obtained, leading to better mechanical properties of material, as no strain hardening takes place, and grain size that we get in hot working is very good or is favorable. We can't say a grain size is good or bad, but it is favorable as in relation to the mechanical properties that are desirable. So, whatever product we are making, we have a favorable grain size, and depending upon the grain size there will be certain mechanical properties of the final product. So, the grain size that we get in case of hot working is favorable, and we get the desired mechanical properties of the final product. Similarly, equipment of lesser power is needed. So, as we have high ductility, reduced strength of the material, the equipment that is required should not be that sturdy, it should not have that kind of fatigue characteristics, or the bed should not be that sturdy. So, equipment of lesser power is needed, lesser power is required for changing the shape of the metal from a raw material or from a rod, plate, sheet into its final form. No residual stresses in the material are present. So, when no residual stresses are present, so some type of failures that may take place because of these residual stresses in the in service performance of the metal or the product that has been formed using hot working, that kind of problem is avoided. No residual stresses are present means the metal or the product is going to behave in its desired manner, and no failure or no fracture etc. is going to take place because of these residual stresses present in the metal. Then hot working also has certain limitations. So, some of the limitations that are associated with hot working of metals are advantages. Already we have seen hot working has certain advantages in comparison to cold working, but it also has certain limitations. What are these limitations? The heat energy is needed. So, we need a furnace to heat a metal before we can hot work it. Poor surface finish of material due to scaling of surface. So, the surface finish that we get using the hot working operation is not up to the desired level. So, we need to go for subsequent machining and finishing operations in order to remove this scale. So, it adds another operation. So, we can see two additional operations have been added. The first one is the heating of the metal, and the second one is the finishing or the machining of the final product after the hot working of metals. Poor accuracy and dimensional control of parts. So, the accuracy that we get of the final product is not up to the desired level or is not up to the specifications, and the dimensional control of parts is also poor. So, accuracy is not good and the dimensional control is not up to the desired level. Now, Other limitations of hot working are poor reproducibility and interchangeability of parts. Handling and maintaining of hot metal is difficult and troublesome, and lower life of tooling and equipment. This may be because of the thermal shock or some other reasons, but the life of the tooling is comparatively less in case of hot working operations. So, now we come towards the end of first lecture on metal forming. In this lecture we have seen that what are the basic manufacturing processes, where do metal forming fit into the manufacturing spectrum, what are the different types of metal forming operations, what are the state of stresses prevalent while undergoing these type of metal forming operations. Then we came on to discuss what is cold working, what is hot working, what is warm working, and in discussing hot working, cold working and warm working, the relative advantages and limitations of all these working operations were discussed, and some of the points were highlighted in details. So, we will start our next session on forging operations. So, we will discuss the details regarding the forging operation in the next lecture. Thank you.